So I'm Matt Greenwolf. I teach here at Carey Academy, and I teach physics. And wanted to talk about a new physics apparatus that I developed on my own that these folks have been using in their physics classes, and your daughter has. And the inspiration for it, and the reason it's in the STEP conference, the inspiration for this actually started with my interest in Montessori education. And I got exposed to that from a friend who was a teacher in a Montessori 3 to 6-year-old class. And just started talking to her about educational stuff. And I recognized that a lot of it was similar to what I was doing in many ways. And then my interest deepened when my daughter enrolled in a Montessori classroom. And I started noticing some of the things she was doing, and again noticing similarities. And I said, well, okay, fine, but what are they doing differently? Because I was really amazed that my daughter would be in this 3 to 6-year-old classroom, and it would be completely quiet, and everybody would be working and totally absorbed and like concentrated. And these are 3 to 6-year-olds, right? I have trouble making that happen with 16-year-olds, right, in my classroom. And so, so I was wondering, what did they do that was different from what I did, as well as noticing the similarities. That's supposed to be a video of broom ball. It just ran on my computer, but it's not showing up here at all. Let's see. Is it just not going to show?
Sometimes if you exit out and just show it in the PowerPoint and then click that, it'll work.
Yeah. All right, I can find it here.
I think I hold the world record for like the longest time
On the broom ball?
Yeah.
What's the world record?
Me. I don't know, whatever I did.
Okay.
I couldn't get it at all.
But that's not the main point. Actually, I clicked on the wrong thing. Let me see if I can find that video. There we go. So this is a student from a few years ago doing broom ball, and the point is, so she's having to move that heavy bowling ball around in a circle with a broom, and she's getting hands-on, active, feeling what force she has to exert to make that thing move in a circle. Which way she have to push?
Towards the ball.
Towards the ball?
Yes.
Okay. Here.
I don't know.
You guys did broom ball, so you
Yeah.
should have felt this. Which way she have to push? I mean, she's obviously pushing on the ball.
Outside.
From the outside in towards the center of the circle, right? Because that ball has some momentum that would take it out of the circle, right? We'll study circular motion later, but they were getting hands-on and getting a feel for it, movement and feeling and actually doing things yourself. Are one of the things that we have in common there. Oh, now it's working. Go figure. Okay. And so there's a Montessori student, also education, very hands-on, active movement, right? All of that, and you look at Braden research and all of these other things, and that is a key factor that's effective in education. Collaboration with peers is a big thing, both in my classroom and in the Montessori classroom. The teacher is off on the side, guiding, instructing, coaching, but the students are inquiring for themselves, figuring things out for themselves, working together, discussing with each other, presenting to the class, right? It's very similar. So here are some physics students working on a whiteboard in a group and putting a solution to a problem down, and there are some Montessori students working some math problems with some physical manipulables. Multiple representations. So this is one thing also that distinguishes modeling physics instruction greatly from more traditional physics instruction, is the really sophisticated and continual use of multiple representations of motion. So here you see a circular motion problem about a merry-go-round and a whiteboard solution that some students did. And in particular, I want you to notice the system schema up in the upper right-hand corner. That's something that you guys will learn in a few weeks, and which you take an inventory of what objects are present and which ones are interacting with each other, and make a clear and explicit choice of your system and separate it from its surroundings. All of that is contained in that one simple diagram, but it allows you to focus on those issues before you go on to the next step and say, okay, what's exerting forces on what direction are those forces, and then how do those forces mathematically combine to solve the problem. So the diagram is helping you to isolate those issues one at a time. There are some Montessori students doing some writing with movable letters so that they don't have to concentrate on the physical process of forming the letters because they're still getting their fine motor coordination and everything worked out. They can just grab those letters and move them around and write. And then they can copy it down. They're using multiple representations to separate out those cognitive tasks and do them one at a time. Okay? In the physics education research literature, one of the key findings from physics education research from the last many years is that we can easily produce students who can grind through equations and ace AP exams and plug numbers into equations and all of that stuff. And then you ask them a simple conceptual problem and they fumble it, right? And the use of multiple representations rather than assuming that someone who can do the mathematical representation and plug the stuff in, which is important, assuming that that constitutes full understanding. If you have multiple representations, they've got to talk about it to their peers, present it to the class, so it's verbal. They have to do it in a diagram and in a graph and in the equations. Then you get a sense of whether they have a really complete understanding. And it was amazing to me when I started doing this, the lack of understanding. I could really see it in my own classroom and the depth of discussion that generated because this pointed out where they were falling short and what we needed to do. And so shifting your information from one diagram to another makes you also translate to your mental representation and back to another representation and make sure that mental representation is fully formed. One thing that modeling has that really sets it apart is the models. This is a picture of, I think, what too many physics students end up with in their head after taking a physics course. Now, it's not like that in the physics professor's head, but the physics students get this collection of equations that they're going to apply to solve problems, and they're just all on one page labeled physics. And by contrast, modeling focuses the instruction in our first year course on 8 general models, and each model gets summarized on one whiteboard with its basic features. And in solving problems, they apply that basic fundamental information again and again and again. So it gets organized and chunked and it's hierarchical and doesn't, and we make sure the students end up with that organized picture in their head rather than just the teacher. So one aspect of Montessori I noticed that was not in my physics instruction was a high level of choice and control given to the students in terms of they get to choose their own work and do it at their own time on their own schedule, and they're monitored for their development of the concepts. And so this is a whole other story, but I've been doing an experiment this year with doing that sort of thing with my own physics students and seeing how that goes as part of, which you may have heard if you were in the blended learning presentation about some of those efforts. But this was another area that I noticed that Montessori was doing something different, that was producing that absorption in student inquiry that I wasn't already doing. And they call this concept control of error, and in particular they mean that the control of error is inherent in the apparatus itself. So here is a Montessori student with some brass cylinders that have to be taken out and then placed back in that wooden block. And they have different diameters and they have different heights. And if you don't place the right cylinder in the right block, you end up with one at the end that just doesn't fit. you don't have to sit down and do a worksheet about height and volume or radius or whatever it is that they're talking about, and have a teacher tell you that your work was wrong and that you got a B on the test or whatever, right? It just doesn't fit if you didn't do it right and you say, huh. And then you go back, and they get absorbed in this because it's at the right developmental level. It's working on a concept that they haven't yet developed, so it's challenging for them, and yet they get the sense, well, I could do this if I can just figure it out. And so when it doesn't work, they're back at it. Nobody had to intervene because the control of error was inherent in the apparatus itself. And so I said, what would a physics apparatus look like if control of error were inherent in the apparatus itself? Right? And so that was the inspiration for me developing my kinematic robots. And here we have one. When the students program the robot, they'll pull up a graphical user interface that I wrote, in which they can draw kinematic graphs. So the top one is a velocity time graph, and the bottom one is a position time graph. And they hook up their USB cable, and they send it to the robot, and it does the motion. So, this one was programmed with that velocity time graph. Okay, so here you go. This, by the way, is the challenge problem on worksheet 2 or worksheet 3 in the constant acceleration model. So you guys can work this yourselves when you're ready. This particular problem was invented by Ginny Rotolo, who used to teach down the hall until last year and was very enthusiastic about the robots. Hold on. So, that was not the right. That didn't do what that graph said. Let's see if I can find it. So you'll get to watch me program the robot here too, so that's good. Okay, so there's that velocity time graph you just looked at. For some reason, when I sent this before, it did not get stored in the robot. So all I do is I make that graph, and yeah.
It's not showing.
It is on.
It looks like this thing is
Is the,
twisted.
It may be broken. If I can get another one. Alright. So now all my students, I was expecting a big crowd and had students come to help assist people in programming the robots when we get to the hands-on part of this, but I'm going to have more students than participants who haven't done this before. Yeah.
I think the wires were.
Yeah.
Alright, lesson in circuitry.
What?
It's just a lesson in circuitry.
Well, I could tell that this was actually. That's the first one of those that's broken in 3 years. So that's not bad. Okay, here we go. Okay, so here's this robot. It's going to do the motion described by that velocity graph. It was right. Yeah, okay, I just stopped it. It was right. Okay, there we go. Now, one of these exercises, we were talking about multiple representations and understanding. So first of all, you have to translate that graph into a motion of an actual object, and you can check that yourself. And you have to know not just what it's going to do, but how far it's going to go and when it's going to change directions and all that stuff. And you can see it happen, and you can measure it. But the next part of this is to check that by programming another robot with a position graph. So there's a position graph which is supposed to match this. How can you tell whether you got it right? Here we go. Now, a student group who sees that knows that their position graph was the right position graph that matched that velocity graph, right? It doesn't need the teacher to correct that problem or tell them whether it was right or wrong, right? The control of error is inherent in the apparatus itself. And when it doesn't work, the response is to push me away. And I've seen it happen many times where I'll say, well, that didn't work, and I'll say, wait a minute, we got to figure this out, right? Since when the control of error was inherent in the apparatus at first, they're like, we've got to make this work. And just like all Montessori theory said, I've seen time and again that students will go back and say, okay, let's figure this out, right? And so that was a particularly complex example there. And another thing that has been very important is a concept called average velocity, which was sort of an appendix, a vestige, in my development of kinematics before. It has become actually a central and really important tool that's changed the way students have solved problems since I've gone with this. And so here's an example of another one. You've got that graph, and you have to program another robot to have the same average velocity. So the average velocity robot is going to have a single constant velocity, but go the same distance in the same time. So here's an average velocity robot. I haven't run these before, by the way, so I let's hope that I got it right. But the control of error is inherent in the apparatus, so if I did the wrong average velocity, I will know. And I did it. Student group who was trying to understand the concept of average velocity and program a robot with the same average velocity would know that they got it after observing that without the teacher having to jump in and say something. So I made a physics apparatus then that had this property of control of error in it and embedded it into the instruction of my classes, and it does enable, just like those preschool kids, more independent inquiry. I can design exercises that have the students explore things on their own, make up a problem. Program this with a velocity graph, program a second, make up your own problem, make up some velocity graph. Program your second robot with a position graph and get it to match. And keep working on it until you can master that skill. And that's the instruction I can give, and they can make their own problems, choose how complex they want to make it, how fast they want to go through that, and keep checking to make sure that they have got understanding. Without me having to have a programmed set of exercises, you've got to work through all of these. Yeah? And so the whole project took a considerable amount of time and effort. This robot, as well as all the other educational robots, are designed to teach programming and problem-solving skills and get the robot to do some autonomous task like run a maze or map a room or go on a particular pattern or something like that. and so they don't have very precise motor drivers. As long as you get the task done in a reasonable amount of time, they don't care whether the velocity was really constant or the acceleration was really constant or whether the velocity really was exactly 12 centimeters per second. As long as it gets done in a reasonable time or the fastest possible time or whatever it is, they're cool. So the motor drivers are not mathematically precise. Generally, the hardware in there isn't ready to handle mathematically precise movement in the educational robots. But I found one that had the right hardware in it, and using the assembly language for the microprocessor, I spent several months making a motor driver that was mathematically precise. And then several more months writing the graphical user interface, which removes the burden of actually writing programs from the students, so that all they have to do is draw the graphs on the screen and send it to the robot, right? And then the robot runs my motor driver and executes whatever graph they sent to it, right? So that they're focused on learning the graphs of the motion, or learning the graphs and how they relate to the motion, which is what we really want them to know. Is this, oh, I'm not. So, some of the advantages for physics instruction, these quotes come from the research literature over the last several decades. Instruction based on actual observation of motion is much more effective. Producing a motion from a graph is much more effective. And going back and forth between the motion and the graphical representation is very effective. All of these are things that you can't do or can't do as well with the other equipment that's available in physics classrooms. So I've got a sample of equipment there. The constant velocity buggy goes with one constant velocity. You can study that and measure it with a meter stick and a stopwatch or a motion detector, the little green box back there, or photo gates there, but you can't tell the buggy, go this velocity and have it do it. Right? It's not programmable. You can't go from the graph to the motion. You can observe the motion, make a graph from it. But when you go from the graph to the motion, that's just a homework problem, right? Not something lab-based that you can observe. So we can go back and forth with this. The buggy goes one constant velocity. The cart on the ramp up there, if I turned it over and put it on its wheels, goes down the ramp with one constant acceleration. I could take this equipment and make something that speeds up with a constant acceleration, goes with a constant velocity, slows down with another acceleration, and it would be a complicated thing with pulleys and masses and things hitting the ground and other stuff. So I would have to set it up, and the students could run it and study the motion, but they couldn't study any other motion, and it would be too much for the students to make their own apparatus like that and study it. It would be a really complex contraption to do it. Here, they can go back and forth from multiple segment motions easily and do a ton more complex motions than you could do with the other equipment and go back and forth. And that's the key of the advantage for physics instruction. The idea, the use of multiple segments in constant velocity motion and the concept of average velocity as represented by the red line up there, and continuing to tie it to actual observation of moving objects, lays a foundation for studying accelerated motion that I have not been able to produce with any other instructional method, so that people are really ready to study accelerated motion when we get there. And as an example, next week, several of these folks will be doing this exercise. Here is a velocity graph for something that has a single constant acceleration and speeds up. And here's a position time graph which goes with just one constant velocity and has the same average velocity. So if I ran it, it would do the average velocity kind of thing that we just did. The one would start slow and speed up, and the other one would chug along, and they'd get to the same place in the same time. That's not really a good approximation to the accelerated motion. It gets the same position in the same time, but otherwise doesn't do the same stuff. So we can do a two-segment approximation. That one's got the same average velocity for the first 6 seconds, so at the end of 6 seconds they'll be even. And then it's got the same average velocity for the second 6 seconds, so at the end of 12 seconds they'll be even. But in between, the accelerating robot is accelerating, and this one's just going constant velocity. Well, we can go with 3 segments. Better approximation. 4 segments. 6 segments. That's 6 straight line segments. Can you get an idea of where this is going? There's the actual position graph that matches the motion exactly. So we're doing a limiting process. We're taking 3 or 4 steps of a process where we gradually approximate the actual graph that would produce this motion a step at a time. And then imagining what would happen after an infinite number of steps. We can't take an infinite number of steps, but in the limiting process, you take a finite number of steps and project to an infinite number of steps, and what would it be? So the whole concept of a limiting process is important, and how that creates this graph is important. And then they have a tool to understand the more complex position time graph that had curves going several different directions and forwards and backwards, because they have built it from a limiting process. And that limiting process, they saw it. It wasn't, in the past, this was, when I went to this point and we had to do a limiting process to see how the position graphs worked for accelerated motion, it was a pencil and paper graphical mathematical exercise. Now you can see it, right, at every step of the way. And so that's just one example of how that foundation from multiple segment graphs in constant velocity motion is a tool that enables them to understand accelerated motion much better. They're really prepared for it rather than having to make a bigger jump. So there you go. That's my presentation. And my idea was that we would spend the last part of this hands-on, having you guys actually program robots for yourselves. And I had a whole bunch of students here. Somebody from the organizing group told me, oh, you'll have like 30 people. So I got a whole bunch of students to come and help. These are expert robot programmers now and have done some of these exercises. And I've got lots of robots here, and I've got some tablets here, but all of their computers have the graphs on. So I guess each of you individually should get with a student or two and work on some exercises. It could be, if you tell them if you want to start simple, you can just start with the first constant velocity exercises that they've already done. If you're a physics teacher, you could do a complicated graph match with position and velocity. I set up Einstein here. Another thing is this interjects some fun. And so I had a capture Einstein practicum here, and these guys have some solutions for it. And I could program the sentries. So the rescue bot has to start down there, and the sentries pace back and forth across here. And they had to program their robot to come up here, get Einstein, and take him back while avoiding the sentries, which made him do a multi-segment position time graph with forwards and backwards motion and different velocities while solving that task. So, the rest of it is for hands-on time and questions, I guess, if people have questions.
Okay.
Questions first, or?
No, dude. Then, yeah, you do some robots.
Yeah, okay, let's do it.
What do you guys teach?
I teach